I'm Lixin. Today, I'm going to tell you how we can do spectrum sensing and analytics in real time across a gigahertz spectrum using only megahertz radios. Spectrum sensing tries to understand how we can use the spectrum. Okay, sorry. Try to understand how we can use the spectrum, and it measures the usage of each spectrum band. And it is particularly important for the government and the industry because it guides the FCC as it tries to set a new set of spectrum policies. And it also enables us to do dynamic spectrum access, which means we are going to use the spectrum more efficiently and dynamically. If we know which part of the spectrum is used and which part of the spectrum is not, we can pick the frequency that is empty and transmit in that band. This is called dynamic spectrum access, and it's believed to be the solution of the ongoing spectrum crisis, and it's believed to be the future of how we're going to use the spectrum. Because of this, there has been 2 decades of work on spectrum sensing. But despite that, we have very little understanding of how the spectrum is used. In particular, I'm going to tell you that today's spectrum sensing systems have big problems. For example, Microsoft have spent a lot of money of deploying spectrum sensing stations worldwide, and it reports spectrum occupancy data like that, which tells you how much percentage of time each frequency is occupied. But it misses important information. For example, this is a radar band. And on that report, it looks like it's not used, it's empty. However, if we focus all of our sensing resources in that particular band, and let's listen continuously, this is what we found. On the x-axis is the time, and on the y-axis is the frequency. As you can see, there is an active signal here which repeats itself. And because it has very low duty cycle, it has very low occupancy, that it is missed by the sensing hardware. And you know what? This is not a rare case. If we look at another band, which is labeled as Air Force, and if we do the same thing, this is what we find. There is an active signal here, which changes frequency on the time, but it is always there, although the report says that it's empty. If you trust the report and think that this part is empty and you transmit, now you collide with the Air Force signals. Good luck with that. So, today's spectrum sensing systems miss important signals, and this can be misleading. But at first place, why this is the case? Why we miss these signals? Why they can't be captured by sensing systems today? In order to answer this, let me tell you a little bit more about how spectrum sensing is done today. Today's spectrum sensing systems have tens of megahertz of bandwidth, but try to capture gigahertz wide spectrum. So what would you do? You do something similar to this, where you hop from one frequency to the next, sensing only tens of megahertz of frequencies each time. This is called sequential scanning, which is very cheap and practical, but it misses important signals. If we do some calculation, we'll figure out that only 1% of the time that the sensing hardware is focused on a specific band, and 99% of the information is missed. And this is not ideally what we want. Ideally, we want real-time sensing with gigahertz wide bandwidth, that we can capture this gigahertz wide spectrum at any time, and we continuously track what is happening. If we do this, we capture all signals. But at the same time, this is very costly because it requires very sophisticated receiver that captures gigahertz wide bandwidth. And it is practically almost impossible for commercial systems in particular. So the question I want to ask is, can we use megahertz radios, which are cheap, but capture all signals across gigahertz-wide spectrum? Is there a way that we can achieve the best of both worlds? With this, I'm going to tell you our system, SpecInsight, which uses megahertz radios but accurately capture gigahertz spectrum. We evaluate SpecInsight in 7 US cities, and we show that it captures very low duty cycle signals that are missed by previous work. So how can we do this? How does SpecInsight work? The intuition we have is that let's scan bands strategically in a manner that we can maximize the probability that we detect signals. Let me explain to you what I mean by this. Recall that we want to have megahertz radios, but we want to capture gigahertz wide spectrum. So somehow we have to sample the spectrum. The question is how we can smartly sample it. And we observe that many parts of the spectrum is used in a predictable pattern. For example, this is a TV signal that we know is always there. So there is no sense of continuously listen to that band. We can just schedule some very brief checks every now and then and make sure that the signal is there. For the radar signal I showed you, we can just schedule brief checks when we expect the signal is there, and some occasional check to make sure that the period doesn't change. Now, we can save a lot of time in these signals with predictable patterns, and we can use all of the time that we saved on dynamic signals that is not so predictable. By leveraging these patterns, we can sense the spectrum much more efficiently. This leads to the architecture of SpecInsight, where we first learn the spectrum patterns, which means we know which signals are predictable, which signals are always on periodic, and what are the periodicities. And based on them, we schedule. So pattern is basically the most important concept in SpecInsight. So you might wonder, what is the exact definition of pattern? We define a pattern as a representative time frequency chunk, which is basically a snapshot of a signal over a short time window like this. By definition, it has two axes, the time axis and the frequency axis. It tells us distinctive information about the signal along two dimensions. For example, this one, it shows us that the signal is always on in time and is narrow in frequency. And another pattern, it shows us that there is a different signal which is discontinuous in time, but occupies the whole frequency bandwidth. So if we can learn all of this information, we can schedule much more efficiently. So how do we learn it? The FCC divides the spectrum into different FCC bands. So we learn them based on FCC band. For each band, we extract what patterns we have in that band. And it might have one pattern, or it might have multiple patterns, because some bands are shared with different signals. Now, for each pattern we extract, we try to learn how often this pattern appears in time by detecting the distribution of the inter-arrival time of the pattern. This distribution tells you whether this signal is always on, whether it's periodic, and how much periodicity you have. At the end of the day, all of this information will go into a database that we maintain and guide us to do the spectrum sensing. So first, let's see how exactly we extract the patterns. For each FCC band, we maintain input signals from the sensing hardware, and we divide them equally in a time. So we end up with these 2D chunks, which has both frequency and time. Of these chunks of signals, some of them might contain the actual signal, and some of them might only have noise. And for the band that is shared by different types of signals, you might have a different type of signal in that band. So the natural question we want to ask is, how we can tell signals from noises, and how we can tell one type of signal from the other type of signal. This is a machine learning algorithm that can be solved by running clustering algorithm on it. If we cluster them, the chunks that actually have signals will be clustered together, and the noises will be scattered. And if there is a different type of signal, it will be clustered into a different cluster. So with this, we can identify the patterns, and after we extract it, we can go on for each pattern and detect the distribution of it. Specifically, we detect the inter-arrival distribution by keeping log of when the pattern appears. And we figure out what is the inter-arrival interval, and we draw the distribution. If the signal is periodical, the period of the signal is equal to the mean of the distribution. And the standard deviation of the distribution tells you how dynamic the signal is. The higher it is, the more dynamic the signal is, and it's harder to predict. And once we learn this distribution, we can go on and schedule based on it. Specifically, let's say that this is the last time I've seen this pattern. So the question I want to ask is, when should we schedule the next sensing? Since we want to maximize the probability of detecting a signal, we want to know when the signal is going to appear the next time. And since we have learned this distribution, we can use it. After time mu, which is the period of the signal, it is expected to appear. And let's schedule the sensing operation at this time instant. So is this that easy? No, because there is also dynamism in the signal. It might appear here or there, or in fact, it's going to appear with high probability a time interval that is proportional to the standard deviation. So in fact, we should schedule our sensing operation in that specific time interval. This is at a high level how SpecInsight works. I've told you that we first learn the patterns, and we schedule based on what we learned. But there is one more thing. If the spectrum is not going to change, this model will work perfectly. But this is not the case. The patterns will change. There will be new users coming to the spectrum, and the old patterns might change. So we have to go back from time to time to update what we learned. And this creates a trade-off between exploration and exploitation. Specifically, how much time we are going to spend to explore and learn spectrum patterns, and how much time we are going to spend to exploit and schedule based on what we learned. This is an exploitation versus exploration problem that in a paper, we mapped this problem to a known problem called multi-armed bandit game. And we leveraged the solution to this game to find the optimal trade-off between them. For the details of the algorithm, I encourage you to read the paper. Now, I want to move on and show you the performance of SpecInsight and share with you some findings we have when we do real-world sensing. First, how we implement SpecInsight. We deploy outdoor antennas and connect them into USRPs, a cheap software radio. And this USRPs covers a frequency range from 50 megahertz to 4.4 gigahertz, and the instant bandwidth of it is 40 megahertz. And SpecInsight is evaluated in 7 US cities, from the East Coast to the West Coast, for 1 week of data. We compare SpecInsight with sequential scanning, the algorithm that is used by today's spectrum sensing systems. And we obtain a ground truth by using 10 USRPs in parallel and continuously monitor a subset of the bands. We repeat this for different subsets of bands. And we report the accuracy of the system by the percentage error of the occupancy reported by each system. This is evaluated with different types of signals, as you can see in the x-axis, always on, periodic, and dynamic signals. The red bars shows the error of sequential scanning, and the blue bar shows the error of SpecInsight. As you see, for periodic signals, we have almost 1,000 times better, and we are also much better in dynamic signals. if we average across all types of signals, SpecInsight's error is 10 times smaller than today's sequential scanning. So why we can achieve this 10x gain, even for signals like dynamic signals, which are not so predictable? The key is that we use the time much more wisely. Specifically in this figure, the y-axis now is the percentage of time we spend in each class. As you can see, sequential scanning simply divides the time equally in each type of signals. But our system divides them very differently. We use minimal amount of time in always-on and periodic signals because they are predictable, and we use all of the shift time on dynamic signals. Statistically, SpecInsight saved more than 95% of the time on dynamic classes. And that's the reason why we have much better accuracy. Not only this, SpecInsight also gives you a much better spectrum report. It gives you the occupancy report like every other system, but as I said at the start of this talk, it might be misleading. In the future, spectrum reports should also contain how the spectrum is used, what signals are there, and how they are repeated, so that it can guide dynamic spectrum access systems. And this is exactly what SpecInsight gives you. On the top, we augmented the spectrum report by spectrum analytics chart, which shows you what signals are in a spectrum. For visualization, we divide the patterns we extracted into the 7 classes, like frequency hopping always-on signals, frequency hopping dynamic signals, and many more. So in a chart, each column corresponds to 1 frequency band, and the rectangles with different fillings correspond to 1 type of pattern. Across the frequency, you pick any frequency band, and SpecInsight tells you what signal is there. For example, this is a fixed frequency, fixed cycle signal that look like this. And there is a white band, a fixed cycle signal here, look like this. So it gives much finer details of the spectrum and also tells you how they are repeated, how the patterns are repeated. More interestingly, if we compare the spectrum analytics chart with the occupancy chart, one thing we can notice is that for this spectrum, for these chunks of spectrum, the occupancy chart is almost empty, while an analytics chart has active signals there. This goes back to what I mentioned at the start of this talk. More than 1/3 of the spectrum is reported empty by this occupancy report by past systems, but it's actually used. There are active signals there with very low occupancy that are captured by SpecInsight. And interestingly, many of this band belongs to government and military. In conclusion, I present you SpecInsight, which can sense gigahertz-wide spectrum using cheap megahertz radios. This is particularly useful if we want to do large geographical scale sensing, because we reduce the cost bar of spectrum sensing. Otherwise, in order to get accurate information, you have to use gigahertz-wide radios, which are very expensive and almost impractical. Second, SpecInsight provides much deeper understanding of the spectrum utilization. We believe it's going to be the start of much finer-grained spectrum analysis. Because of that, we also believe SpecInsight is going to be the key primitive for future dynamic usage of the spectrum. Thank you very much, and I'm happy to take questions.
Hey, Aaron Schulman, Stanford. So is it possible for you to mark the bands where point-to-point links are used, for instance? And because those you probably wouldn't be picking up from your one omnidirectional antenna. Is there any way that like in the FCC charts you could look up and say, yeah, these bands are used for point-to-point links, so if we say there's 0 occupancy, we're probably not right about that because our antenna is likely just not in the middle of that point-to-point link.
Excellent question. So the goal of SpecInsight is to provide you a tool that you can see what is happening in the spectrum. And after that, you can try to analyze what patterns you get, and then you'll see whether it's point-to-point or whether it's directional. So we are talking to FCC now about analyzing the patterns we extract and what sources they exactly mean, like whether they come from directional antennas and what technologies are there.
And also, really, oh, you have a question? Go ahead. Sorry.
It's okay.
Just really quick. Did you dig into the signals that you saw, for instance, the ones that were really confusing? Did you actually, for instance, just look at the waveform and see if it's a waveform that you recognize?
Yes, we look at our signals, and we make sure that we see the signals in multiple locations.
Okay, thanks a lot.
Very nice work. Yan Zhuang from University of British Columbia and NYU. I'm just having one question about assumption of your model. Do you assume all the signal spectrum distribute as like the bell-shaped Gaussian distribution?
No, we don't have any assumption about the distribution of
But
spectrum.
I remember on one of your slides you showed there's like a mean and a variance, and that seems to be the Gaussian distribution. Have you considered whether that's a practical and realistic model?
So we don't assume the distribution to be Gaussian. The reason why I show you this is we just need to have some visualization of the distribution. We don't have any assumption that it's Gaussian.
I see.
Yep.
So there's no like, anyways.
It can be any arbitrary distribution.
All right. Thank you.
So I have a quick question.
Mm-hmm.
So how sensitive are your results to location?
That's an excellent question. So there are patterns that you can see across different locations. These are like these widely used signals like TV signals and other type of signals. But there are also patterns that are like specific to a specific location. That's because naturally some signals are in this location, and in other locations the signals are going to be different.
I was wondering, does your accuracy depend on location in some particular way, or where you are in one of these cities that you measured?
We look at the accuracies for different cities. They are roughly the same. Although you get different signals, but on average, they're roughly the same accuracy.
Any other questions? I had one more question for you. So in terms of the explore-exploit algorithm that you described, what is the time scale and sort of this operation? It doesn't seem like this is something that you would need to do at very fine time scales. So I'm just wondering, how much does explore-exploit really matter, and at what time scales?
So all of the sensing operations are in millisecond.
Okay.
So we basically algorithm decide which band to pick iteratively, and each iteration takes like millisecond. So you spend that amount of time in each band, and you move to the next. That's the time scale we're talking about.
And explore-exploit is also operating at the millisecond time scale?
So you can think of that way. So each is an iterative algorithm, and each time you try to pick which frequency to sense. And each time you make a decision, you have this trade-off, and the trade-off algorithm will tell you a solution.
Okay, let's thank Lixin once again.
Thank you.